Yeah, from UBC. We talk about the universal electronic structure of layered nickelates via oxygen-centered planar orbitals. Yes, keep going. Let's going.
Okay, thank you. Thank you for the introduction. I'm Christine Au-Yeung. I'm a PhD student of Andrea Damascelli from UBC. I'm very honored to be here to share with you all our recent work on the 327 nickelates. Okay. So a brief overview of the nickelates family. The entire family is actually very interesting. So the building block of this family, it's this nickel oxygen octahedral. And then if we only have a single one of them in each layer, and it is a single layer 214 nickelates, and it's known to be a Mott insulator. And if you stack more of these building blocks together, then we have this 327 bilayer nickelate. And then now the valence of nickel decreases as you stack more layers of this octahedral together, and it's 7.5. And you can also stack them all the way together, and then you will get this infinite layer 113. And so when we increase the number of layers, we decrease the number of valence, but at both ends from D8 to D7, it has a tendency to be an insulator. While in the middle, and then we term them together as the multi-layer nickelates, they are superconductors under pressure. So the multi-layer nickelates are actually quite, so the structure is different, but then they actually share a lot of common properties. For example, they are both superconducting, and they're both known to be having some charge or spin density wave transition. So for our study, we're mostly focusing on 337, but at different points, we'll try to make references to 4-3-10 systems as well. So before I show you our RPES data, I want to first show what would DFT predict the band structure would be. So this is a 2222-327 band structure calculation. This is a plain LDA calculation without U. So without U, we will see first this alpha pocket, the beta pocket, and the gamma pocket will cross the Fermi level. But if I add, say, for example, 4 EV of U, and this gamma band will shift below the Fermi level, and the pockets will be slightly smaller to be stoichiometric. So as we all know now, the 327 also has a polymorph, which is a 1313 stacking. Just by DFT, you can see that we predict that the Fermi surface will be quite a bit more complicated than the 2222, 327. And we have more bands. And we can also compare to 4310. Also, it is more complicated than the 2222. Okay, so here's our data. We get our crystal from John Mitra of the Argon group. And so this is a nice single crystal, but we know that there will be a polymorph of both 2222 and 1313. We want to use RPES to see what would be the difference of the Fermi surface or the electronic structure, but then we don't know where they are. So what we end up doing is that we use our RPES to probe the entire crystal all over the place. And then we have a map of the bands of each single point of this crystal in real space, and we find a very homogeneous region, and then we would take data from this region. And after that, we send this crystal back to Argon group, and Xinlong, he did an amazing job in extracting this tiny little bit of crystal where we actually made our measurement. And then they did XRD to confirm what is the structure, whether it's 2222 or 1313. So from our data, we are able to distinguish the 2222 and 1313 electronic structure, but only in the valence band. But then if we go to the Fermi surface, Baiyang did already make a preview of our Fermi surface. And for the 2222 and 1313, actually the Fermi surface, they are very similar. So we have the alpha pocket, a beta pocket. This beta prime pocket is the folding because of the tilting. And other than that, they are basically identical, apart from a small difference in the electronic volume. This volume, we are calculating the area of the electronic nature of this Fermi surface as a ratio of the Brillouin zone. So in RPES, we can also try to understand the dichroism, then we can get the symmetry of the first electron removal state. What I'm showing you here is the geometry of our measurement. So this blue square is the scattering plane, and we are orienting our sample as that this scattering plane is at 45 degrees to the nickel-oxygen bond. And LV is basically the factor that is parallel to the sample surface, and LH is the factor that is parallel to the scattering plane. So this would be like a typical x squared minus y squared orbital. And this is a diagram result, just to remind you that this blue arrow is the direction of the nickel-oxygen bond. And this is a LV minus LH diagram, so red is positive. We can also make this representation a little bit more quantitative by taking this gamma as 0, and then we can integrate the intensity of each angle, a polar angle towards this Fermi surface, and then we'll get this polar plot. And the red is LV, and then the blue is LH. To extract the physics, and we need the help of a tight binding model so that we can simulate the matrix element effect to see what is the symmetry of the first electron removal state. And the first thing that we will try is similar to the tight binding model that was shown in the previous speaker, that we have the x squared minus y squared and c squared orbital as a starting point. So the band structure itself looks very much like experiment. It also reproduces very nicely the Fermi surface. However, the diagram is wrong. We cannot get the same diagram as the experiment. As it turns out, what can reproduce the diagram of the experiment is that in the tight binding model, we also need to add the sigma bonded oxygen p orbital in our tight binding model to be able to have the same diagram. And I'm going to show you why. First of all, if you have this c square orbital, you would just think that, okay, this c square orbital will have a very strong outer plane polarization. But I'm showing you this Fermi surface at this similar to the cuprates pi half point, and then we have this Schwarzschild singlet-like orbital. This is like a monocle orbital with the symmetry of a Schwarzschild singlet. We have this dxy orbital, and then also with the phase matching of the p orbital around it. But if we follow the evolution of the first electron removal state wave function at around the boundary, and this c square orbital character will be mixing into the x squared minus y squared. It ended up being a 3x squared minus r squared. And this is a nickel. And this nickel can be strongly hybridizing with the p orbital of the oxygen. And if you look at it like this, it looks like this 3-spin polaron, so that this oxygen is actually coordinating and hybridizing with 2 neighboring nickel. So the important thing is that to give this right diagram, the wave function actually, the extended wave function actually remains in plane. So now I'm going to sidetrack a little bit to mention about the other member of the multilayer nickelate, which is the 4310. And this is the Fermi surface taken in the literature at 98 eV. The striking thing that you will see is that although the structure is different, but the Fermi surface is very similar between 327 and 4310. And this is not only the only similarity we found. If we look at all the 75 eV photon energy data, there is one thing very interesting, which is this corner feature that appears both in 4310 and 327 system. This feature is very photon energy dependent. So if we use our 100 eV photon energy, we don't see it, but 75 or 45, we will see it very clearly. So at the very beginning, people will attribute this as like an impurity state or some surface effect. But I'm trying to convince you that this feature is way more interesting. So this is a Fermi surface that we took using 45 eV. What I show you here is the original beta band, and this corner thing is what I am interested in. This is a cartoon picture of this Fermi surface, and I want you to look at this highlighted purple region of the beta band. If I translate it like this, and then I will produce a T-beta band. And it's not just the shape of the band that get reproduced, actually the entire dispersion when we follow below the Fermi level, it actually really reproduced the original beta band. And the translation factor of this is a 0.61. So two things immediately pop up in our mind. Firstly, is that this is a very suggestive Fermi nesting situation, and whether this translational symmetry breaking may be related to spin density wave, because it is indeed the direction and similar magnitude of the spin density wave. So we ask ourselves, if it is because of Fermi surface nesting, how many ways we can nest this Fermi surface? It turns out there are two of them. And we calculated the autocorrelation function as a function of doping. And then we can get two of these Q factors that would change as a function of doping. Next, we look at the literature and trying to extract the Fermi volume of the published RPES data and compare the translation of the beta band. And we put it in this plot. The first thing that strikes us is that even within our own data, which is the blue dots that we have, that is quite a big spread in terms of Fermi volume. The second thing is that, of course, it fits very well with the Q1 factor, which is this nesting factor that we're talking about that would reproduce the T beta band. And there are also like a spin density wave translation factor that was published, and for 327 and for 310. And then our translation factor is right within this range, so that we have this connection between the translation of the T beta band and also the spin density wave for both 327 and for 310 systems. And so I go back to our dichroism result. We concluded that in the Fermi surface first electron removal state, we have basically two molecular like orbitals, which is one having the sunrise singlet-like symmetry, x squared minus y squared, and the three spin polaron-like. So which one of them will be responsible for the spin density wave? So what we can figure out is that we can try to project the density of state of this orbital, this x squared minus y squared orbital, and see where are they in the Fermi surface, and we can do the autocorrelation calculation again. So the result is what I show here. Without doing the projection, we will see both Q1 and Q2 factor. But if I do the autocorrelation only on the projected Fermi surface, I will only get Q1. So that now we can conclude that the orbital character that is mediating the spin density wave should be this sunrise singlet-like symmetry. The next thing that we find very interesting within our data is that part of the Fermi surface is gapped out. This alpha pocket is gapped out. And not only that, the size of the gap is actually a function of doping. So when we decrease the electronic volume of the Fermi surface, and the size of the gap also decreases. And I think it's maybe reasonable for us to attribute this variance in the Fermi volume as a function of oxygen content. And when you have more oxygen content, you will have less electron volume. And we see that that is a smaller gap. What I'm going to show you is that this gap opening is actually also a signature of the spin density wave. When I show you this cartoon Fermi surface, maybe you already having a question about when we shift this beta band, what happened to the rest of the thing that we don't see? And the answer is that it gaps out. To show this, we can use our tight binding model, but then we extend it to a supercell of spin density wave. So now I'm not showing the oxygen, I'm not showing the nickel, but then I'm only showing the oxygen orbital. And what we did is that to mimic the spin density wave, we are putting a very small magnetic moment on plaquettes of oxygen orbitals. So the nickel is in the middle, and then this is a net negative magnetic moment in this plaquette. And the red one is the net positive magnetic moment in the plaquette. But if we arrange the oxygen orbitals like this, and it will give you a very natural up zero, down zero order of the spin density wave, which is what was reported. So now this is our unit cell, as I highlighted. But the important part to reproduce the experimental gapping out is that if you have a bilayer model, your top and the bottom layer has to have a different order, so that you have to be an antiferromagnetic coupled bilayer to be able to open the gap. Otherwise, the symmetry would not allow you to open the gap around the alpha pocket. And if I have a higher magnetic moment, and I will have a bigger gap, and I have a lower magnetic moment, I have a smaller gap. So here, hopefully I show you that both the spectral gap opening and the T beta band are both signature of the spin density wave. But more importantly, we actually make a connection between that as a function of doping, how it is actually suppressing the spin density wave. And as from all the literature right now is showing that oxygen is very important in terms of superconductivity, then maybe when we have a more and more increasing oxygen content, this is where superconductivity will emerge from the material. So the last thing I want to show you is that we are dealing with both 2222 and 1313, but then the minimum model that can reproduce a diagram from our experiment is a bilayer model. So this bilayer model is very, very similar to what we've seen before. The only difference is that we are adding this oxygen orbitals to reproduce the nice diagram. But in terms of 1313, it's getting more complicated because the DFT doesn't predict the band structure should be like this. But then from DMFT calculations published, and then we see that there is a tendency for the charge transfer between the inner plane of the trilayer to the monolayer. And I've shown at the very beginning, actually through the entire doping, both D8 and D7 there tend to be insulating. And then we are thinking that, okay, the monolayer is closer to D8 and maybe it's just gapped out. And the inner plane, because it's closer to D7, we can also remove them from the Fermi level. And it ended up, we only have two bands crossing the Fermi level, and it will give the same diagram effect as the bilayer model. However, when we move away from the Fermi level, of course, the bands will be very different. And it's also shown in our data that the valence band of 1313 and 2222 are different. And so what we're suggesting is that the reason why 1313 and 2222, they're so similar, maybe that this is a layer-dependent Mott transition to make the low-energy physics very comparable between the two systems. Okay, so this is the end of the presentation. Our conclusion is that the nickelates, they share common electronic structure. I'm talking about the multilayer nickelates. And then the important reason is that there is a layer-dependent Mott transition, and the minimum model is a bilayer model. The low energy physics is dominated by planar orbitals of the oxygen, and the one that is responsible for the spin density wave is the strongline singlet symmetry molecular orbital. And last but not least, let me thank our collaborators, Xin-Long Chen and John. They did an amazing job in helping us through the entire experiment. And we also have our marvelous postdocs, Dave Smith and Martin Bruske. In terms of theory, we have our own George Savasky, Mona, and Ilya, and all the experiments were taken in the Canadian Light Source QMSC with the help of the beamline scientists, Martha and Sergey. So thank you very much. I'm open for questions now.
Yeah, thank you very much. So last night, let me ask the first question. Last night, I think Meng Wang showed that the TC for the 133, right, compared to this 327 is much lower, right? Even when you put pressure. So how do you understand that from what you're saying? The electronic structure is rather similar in these two systems.
So we are not extremely sure because all these measurements that we did is from like a normal state. I think that we are talking about a normal state electronic structure, but when we add pressure or when we are talking about like more correlated states, it might show a difference. But then the point is that from our data, we think that the electronic structure, the basic electronic components are different, but there might be some not obvious ingredients that we are not very sure yet. This is as much I can tell.
Okay. Yeah, thank you. Yeah. Any other question for Christian? Yeah, this is a very, very interesting talk. Yeah. So basically, it doesn't matter what structure you have, right? It's very, very similar. Yeah. Yeah.
Yeah, this is from what we've seen in terms of RPES. Yeah.
Any other question?
Maybe I can ask. Okay, I can jump in and ask one.
Please.
Briefly.
Yeah, please.
This is Barrett. Thank you for the nice talk. And again, I'm sorry if I missed this or if you've just repeated yourself, but I know that previously they had done some very nice RPEs on the tri-layers. So did you compare like the bilayer to the 1313 to the trilayer, and is it all really part of this same series?
Oh, so we haven't done so ourselves. We haven't done the tri-layer RPES, like as we're not shown here. We compare with what we've seen from the published data. So from most of the published data that we've seen, the Fermi surface is very different. The same number of bands, and they also show the T beta bands. Yeah, so the comparison is they are almost identical. Yeah.
I see. Okay. Thank you.
Thank you.
Henry? You're muted.
You're muted.
You're muted, Henry. You're muted. We cannot hear you. Yeah, I think he noticed. Yeah. Yeah, go ahead. Yeah.
Yeah. If I understand what you say, there is no big difference between this compound and the 123 IPCO.
So
yeah, that's what she says. Yeah.
Yeah, so we are talking about the low energy physics, like in terms of RPES, as long as the Fermi surface is concerned, they are very similar. But there would be difference, as we've seen, there are differences in the lower, like the valence band. They are very different.
Okay.
Yeah, but the superconductivity seems to be the same.
So the TC is different for between
quite a bit, yeah.
Yeah.
By like almost an order of magnitude, right? More than an order of magnitude, yeah. Mm-hmm.
Yeah.
Okay, Chimel, you have a question? I see you turning on.
Well, yes. So I guess just along similar line, I'm not too familiar with the 1313 system. Is there also density wave like order in the 1313 case?
As far as we know, yes.
And
But of course, it would be very also dependent on how the sample was grown, whether it's oxygen deficient. But from our samples, yes.
But is the wave vector ordering wave vector similar?
Yes, from our sample, yes.
Okay.
So it is doping dependent. So it's like for us, as I shown maybe earlier. So we have plotted all our data here, so that this is the translational symmetry.
Yes, that's what you said. Okay.
Yeah, so this is similar. But then I think in terms of like whether there's a phase pure 1313 spin density wave calculation, like scattering experiment or something, I don't remember seeing that. So I think most of the data that we see from neutron or from scattering is from the bilayer model.
Yeah. Amongst that, there's no neutron data yet for the Au-Yeung data for the single 1313. George, you have a question?
Thank you. Yeah.
Hey, George.
Hey, George. Yeah, we cannot see you, but you're muted.
It's still good.
There we go.
Oh, there you go. Yeah, thank you.
Hi, George.
My camera doesn't seem to work. Anyway, so it had to do with the difference in TC between the tri-layer, shall we say, and the bilayer. That of course could be. I mean, we have. If we think the outer layers in the tri-layer are the superconducting layers, they could be superconducting pairing within each layer, within the two outer layers. They could be two superconductors, shall we say, which are weakly coupled in the case of the tri-layer. But in the case of the bilayer, they could be much strongly coupled. Actually, that would be consistent with what Au-Yeung, for example, says, because he has, in his theory, both, that was for a bilayer, he has both coupling within the layers themselves and coupling between the layers. And in that case, the coupling between the layers, if I understand it correctly, is quite a bit stronger than the coupling within the layer, or the pairing within the layer. Okay. So that could be the reason. Actually, that would be very interesting if one could investigate that.
That would be
okay. Yeah, thank you. There was also a comment by John Mitchell, who's saying that as far as he knows, no one has actually observed any, a wave vector, ordering wave vector for the 1313 including them, but people are still trying. So basically, I mean, Meng showed last night, right? There was some transport anomaly, but basically there's no spectroscopy evidence of any sort of a wave vector known either spin density or charge density wave. That's the current situation.
Thanks, John.
Yeah. Okay. Hey, Mike. Yeah.
Well, I'm sort of curious why you guys are worried about this, right? Because I think all the experiments seem to indicate that in the 1313, the monolayer is basically insulating. So the electronic structure for the 1313 looks very similar to the trilayer. So I would expect you're not going to see much difference between the two.
I see. But why is TC so much lower in the 1313 when you put pressure on? Meng claimed the 3K, right? Last night.
Well, there's a lot we don't know, right? There are claims that you have a density wave,
Right.
density wave in bulk to be able to see superconductivity under pressure. Yet the films, as far as I know, no one's seen any evidence for density wave in any of the films. So there's a lot of mysteries.
Yeah, it's all. I mean, I guess mostly material problem. I cannot make it really pure.
Plus, everything is probably very sensitive to the
Oxygen.
oxygen stoichiometry, which I think
Which is
still
George's
not as
point,
well
right?
understood as people claim it is.
So can I follow up on this, Pinching?
Yeah, sure.
So, I mean, irrespective whether the density wave is driven by nesting or by some other mechanisms, if the wave vector match, then you should see some feature, which is what you emphasize. But is there some gap-like feature in both the 327, both the 2222 and the 1313?
Yes. So then let me show you. So these two are 1313, and this is a 2222 sample.
Yeah. So, but at the tip of the beta band, if you look at the spectrum, if you look at the EDC, do you see some gap developing that's associated with the order?
It seems to be.
You mean in the beta band?
In the beta band at the tip, at where the wave vector matches.
Right. So from our model, actually what we are showing here, and then it is like a one domain. So when we overlap like this part to this part, and then this entire overlapping region should be gapping out, including the beta band. But then the reason is that each domain is very small, so that you're basically having two orthogonal domains together. So the result is that we'll only be able to resolve the gap around this area. And then this one will be like one side of it will be not gapping out, and that's why we don't see the gap opening.
No, but that's fine. But in that area, if you look at the EDC, you do see. Oh, I see. You're saying the feature is already seeing the gap. You're already wiping out the Fermi surface. Thank you. Yeah.
Yeah, and maybe Jimiel, if I can add, if you look at the middle panels, this is band dispersion taken along that cut highlighted in orange in the Fermi surface panels.
Yeah.
Right, and you can see that on the left-hand side, there are two bands that reach the chemical potential, but the two inner bands do not. And so if you look at the MDC at the Fermi energy, you see that on the left-hand side, you have only two peaks at the Fermi energy. On the right-hand side, for the highly oxygenated sample, say, you have four peaks. So that is directly the gap. So there is a gap.
Okay, great.
So the gap is there and presumably will be there in a much bigger portion of the Fermi surface. But then because of the domain, as Christine was saying, when you have two rotated domains, then it becomes evident in these non-high symmetry positions, but the gap is there.
So then
presumably it will be temperature dependence, which we have not done in this particular work yet.
But this gapping out is similar between 1313 and 2222.
Yes.
So that would suggest that the density wave vector better be comparable in the two cases.
Right. So basically, when you were saying, is there any evidence? Well, if you take as a spectroscopic evidence our work,
yes,
and the previous plot where Christine was putting all the Q vectors versus doping, well, there is a spectroscopic evidence of an incommensurate spin density wave, which is in all of the systems. So 2222, 1313, and 4310, the Q vectors are the same as far as the symmetry. They differ in magnitude, presumably because of the fermiology, the volume of the Fermi surface.
I mean, this is beautiful, but I mean, I wouldn't necessarily imply that the driving force for the order is the Fermi surface nesting, because basically any mechanism that leads to that order with that wave vector will open up gap-like
Right.
features on
I fully agree with you. I mean, in fact, I make this point even more strongly. If you look at cuprates,
yeah.
and you look at the charge order in cuprates, you extract the same relation between the charge order and the Q vectors in the fermiology. But sure enough, I wouldn't believe that to be due to nesting. Okay,
Yeah.
so
But
certainly
it's beautiful. Thank you.
but certainly
I didn't
there is.
appreciate that. Yeah.
Maybe
Okay,
the last point I'd like to highlight in this relation here, basically what Christine showed with her work is that the orbitals, these molecular orbitals with an x squared minus y squared symmetries are involved in the spin density way clearly. Those are the ones which are, the Q vectors connects and the ones which are gapped. What is interesting, as you increase your oxygen content and superconductivity comes, now emerges, those states are coming back to the Fermi energy. So now they're no longer gapped. So to me, it sounds like not only, oxygen is scaling the spin density wave and allowing superconductivity to emerge, but those x squared minus y squared orbital would have to play a role in both. That would be my, my extrapolation just from the phenomenology.
Yeah, this is fascinating. Thank you.
thank you.
Sorry, Michael. Mike, you had a question maybe at one
Yeah,
point?
Mike probably won't have the last word.
Well, I was going to say, I mean, if you look at the Hall data on these materials, you remove a large part of the Fermi surface when you go through the transition. So this is sort of well-known independent of spectroscopic data. And I also wanted to point out that there were two tri-layer ARPAS papers on the archive the last 2 nights.
Yeah.
Okay.
That's right.
Which look at the gap opening up in great detail. So
it looks consistent though, the picture.
yeah.
Yeah.
Okay. Yeah. Thank you all. Yeah, we'll see you tonight.